Okay, we are halfway through the synthesis session. So far, we have seen how to use synthesis to build various good things. The next talk, Tom from Technion is going to tell us how to attack neural nets using program synthesis.
Thanks for the intro. Good morning, everyone. I'm Tom from the Technion Israel, and today I will be presenting our paper, One-Pixel Adversarial Attacks via Sketch Programs. This is a joint work with my advisor, Dana Drachsler-Cohen. Let's begin with some background about one-pixel adversarial attacks. In essence, this attack takes an image, for example, a dog, that's accurately classified by a pre-trained neural network. But then, we perturb just one pixel, and this tiny change, like turning one pixel purple, as you probably can see here, make the networks to make a mistake. So in our dog image example, after we perturb one pixel, the network misclassifies it as a cat instead of a dog. There are two main challenges to overcome for successful execution of these attacks. The first, and maybe the most obvious one, is the extremely small perturbation region. You can see examples here in the slide of successful one-pixel attacks on images from the ImageNet dataset. Take, for instance, the image at the bottom right of the slide. The attacker perturbed only one pixel, here highlighted with the red circle, which is only 0.002% of all pixels. This small perturbation was sufficient to mislead the network into classifying this image as a nipple instead of a hamster. The second challenge lies in the non-differentiable nature of the perturbation. Unlike other adversarial attacks, like L-infinity attacks, where the attacker can introduce minor epsilon noise across all pixels, one-pixel attacks require the precise selection of the pixels to be perturbed. Therefore, one-pixel attacks are unfit for the usual methods of continuous numerical optimizations and have to rely, in most of the cases, on discrete optimization strategies, which tend to be more computationally intensive. As a result, most existing one-pixel attacks rely on either local or random search. In these methods, the attacker constantly submits perturbed images to the network, which are referred as queries. The process iterates until a successful attack is achieved. For example, at this point, the network is misclassifying the image of the dog as a cat. The results of this optimization process is that existing attacks pose a very large number of queries to the network, making their attacks very expensive or even infeasible in real-world settings where the networks limits the number of queries. For example, many online classifiers allow the user to pose a limited number of queries for free per month, and then the users need to pay for every extra query. For example, you can see here the Microsoft Azure Vision API pricing, which allow at most 5,000 queries for free per month. All of this raises the question, can we compute one-pixel attacks with only a few hundred queries? So now we can define our problem. We have a pre-trained neural network classifier to which we have only a black box access. This means we can only feed inputs and receive the final probabilities output vector with no insight into the internal layers and gradients. So given an image that is initially classified correctly, our goal is to compute a one-pixel perturbation that causes the classifier to misclassify the image. Crucially, we aim to achieve this with a minimal number of queries to the classifier. In addressing this problem, our approach leverages program synthesis to compute one-pixel attacks. We have called these techniques OPPSLA, not OPPSLA, don't be confused, one-pixel program sketch for adversarial attacks. The core of our approach is built on three key pillars: the sketch, the conditions, and the synthesizer. Let's begin with the sketch. The main idea behind the sketch technique is to allow us to create partial programs that outline the intended implementation strategy. This approach leaves some parts of the low level of the implementation to be filled in by an automated synthesis procedure. In our context, and this is one of our key ideas, we have designed our sketch to construct a program that dynamically prioritizes possible one-pixel perturbations. These conditions that govern this prioritization are left undefined. These are the holes that our synthesizer is tasked to fill. Let's see an example. We initialize our program with a queue containing all possible 1-pixel adversarial examples. The prioritization of this is defined for every pixel location and for every corner of the RGB color cube. First, we pop the top element from the queue. For instance, in our case, it's an adversarial example involving a blue perturbation of the pixel in the center of the image. This perturbed image is then submitted to the classifier, and if the classifier misclassifies it, it returns this adversarial example. Otherwise, we move to assess for condition. If the first condition evaluates to true, we push to the back of the queue adversarial examples featuring the same perturbation, but at adjacent locations, as you can see here. Then we check the second condition. If it evaluates to true, we push to the back of the queue the first adversarial examples in the queue. The next adversarial example is in the queue that has a perturbation in the same location. Again, in our case, it's the center of the image. After potentially pushing examples to the back of the queue, we evaluate the third condition, and if it evaluates to true, we push adversarial examples with the same perturbation at adjacent locations to the front of the queue. Lastly, our final condition, if it evaluates to true, we push the first example in the queue that features a perturbation at the same location to the front of the queue. Again, in this iteration, it's a perturbation in the center of the image. So basically, we have two conditions for pushing adversarial examples to the back of the queue, and two conditions for pushing adversarial examples to the front of the queue. So now this is the state of our prioritization queue after the first iteration. Next, we start a new iteration by, again, removing the top element from the queue, submitting it to the network, and if necessary, checking the conditions. This process continues until we either find a successful adversarial attack or explore all possible 1-pixel perturbations. Let's now talk about the conditions that determine the dynamic prioritization in our approach. The conditions take the form of a comparison between a constant R and the function f. There are few possibilities for what this function might be, which are all based on previous post-hoc analysis of 1-pixel attacks. Firstly, f could compute the minimum, maximum, or the average value of the RGB's value of the pixel that is being perturbed. For example, this kind of conditions might lead to a prioritization of perturbations in the darker regions of the input image. Another option is a function that measures the distance of the perturbed pixel from the image center. Finally, a third type of function might quantify the change in the network's confidence in the correct class before and after the perturbation has been applied. Now we can represent any program as abstract syntax tree that contains the details about each condition. Let's see an example of a program. Assuming that we tried the given adversarial example and it wasn't successful, unfortunately. Now the first condition leads to pushing nearby pixels to the back of the queue if the confidence difference before and after the perturbation is below 21%, while the third condition leads to pushing nearby pixels to the front of the queue if the same confidence difference is above 25%. Also, the second condition leads to pushing to the back of the queue the next adversarial examples with the same perturbation location if the perturbation pixel has an RGB channel that is above 0.19, meaning it's not a very dark pixel. Let's now examine our synthesizer, which employs a stochastic search inspired by the Metropolis-Hastings algorithm. I want to emphasize here that the main challenge of our search stems from the fact that the condition language consists of both Boolean constraints and real-valued variables and constants. So as a result, the condition language is both infinite and not suitable for standard numerical optimization. So our synthesizer operates using a training dataset consisting of up to only 50 images, which is a fairly small number, a pre-trained neural network, and an initially random prioritization program. We start by evaluating the score of the initial program. This score is inversely proportional with the average number of queries needed in order to achieve the successful 1-pixel attacks on the training sets that I mentioned earlier. Next, our search algorithm selects a random node in the program's AST and mutates its subtree. This mutation replaces each node with an element of the same type, and therefore constructs only trees corresponding to a well-typed programs. Then we compute the score of the mutated program P prime, and next a random number between 0 and 1 is generated. If this number is smaller than the ratio of the new score of program P prime to the old score of program P, we retain program P prime and discard program P. This means that the fewer the average number of queries of P prime compared to P, the larger the ratio, and therefore the higher the likelihood of replacing P with the new program P prime. We iterate through this process until we either achieve convergence or hit a timeout. We evaluate our tool against two different one-pixel attack frameworks, which includes PLDI'23, known as the state-of-the-art in maximizing the success rate, which is the proportion of test images successfully attacked, while also minimizing the number of queries submitted to the classifier during the attacks. We conducted the attacks on the CIFAR-10 and ImageNet test sets, and additionally, we applied different query limits during these experiments. I would like to highlight 3 experiments conducted on 3 distinct CIFAR-10 classifiers. The plots you can see here each correspond to a different classifier with the number of queries on the x-axis and the success rate on the y-axis. Our tool represented by the red line. As illustrated, when restricted to a 100 query limit, our tool outperforms by 59% in terms of success rate the current state of the art, which is PLDI'23. We have also assessed the transferability of our tool. And our findings suggest that even when an adversarial program synthesized on one network is transferred to other network, the number of queries remains significantly lower than those seen in existing one-pixel attacks. This implies that the attacker would not need to synthesize a unique adversarial program for each individual network. Clearly, the synthesis process requires a high number of queries to the classifier for the synthesis process. However, the process is performed just once for a specific classifier and a training set, so then users can apply the adversarial program to as many images as they want. Having said that, we have found that approximately 50,000 queries are typically sufficient to synthesize an effective adversarial program. To summarize, we have addressed the challenge of generating one-pixel adversarial attacks with a relatively low number of queries. We developed a sketch for a prioritization program and a domain-specific language for conditions that govern this dynamic prioritization. Additionally, we implemented a synthesizer that utilizes stochastic search inspired by the Metropolis-Hastings algorithm with the goal of minimizing the number of queries to the classifier during the attack. And finally, we demonstrate that our tool, which is publicly available, of course, achieves a state-of-the-art success rate while significantly reducing the number of queries. Thank you very much for listening, and I'm ready to take some questions.
Thank you, Tom. We have plenty of time for questions.
Hi, interesting talk. So in your evaluation, you showed that you were able to find one-pixel attacks faster as compared to the previous tools. My question is, if a previous tool successfully found a one-pixel attack, was your tool also able to find a one-pixel attack in all those cases?
Yeah, our tool, in comparison to the state-of-the-art, which is PLDI'23, our tool would definitely find, if a successful one-pixel perturbation exists, our tool would find it, same as PLDI'23. This is only a matter of how fast you can reach to a successful one-pixel attack, and not to the overall success rate, if you have unlimited number of queries.
Okay, thank you.
Hi, Tim, Princeton. I was wondering about the scalability of your tool with respect to the size of the image. How does the size of the image and therefore the number of pixels in the image affect your ability to find good attacks?
Yes, thanks for the image. So I've been asked about the scalability of our tool for larger images, not just CIFAR-10. So in the paper itself, we evaluated it also for ImageNet images, and we have found out that it actually works also for ImageNet. Of course, it's much harder than CIFAR-10, but it can also be applied for larger images.
Thank you.
Hi, thanks for the talk. Cole from UCSD. So I'm going to preface this by saying I don't know much about image classification, but it seems to me like if you're like 20%, if the classifier is like 20% confident that something's a dog, it's probably easier to trick it than if it's 100% confident that something's a dog. Did you compare the performance by like a bucket of like 20% about confidence
Can you
near
get closer
100?
to the mic?
Yeah, sorry. Do you want me to repeat the question?
Repeat the question, please.
Yes. So did you compare the performance based upon like buckets where there was only like 20% confidence that something was a dog versus some buckets where there was like 100% confidence that it was a dog, and the number of queries that differed between the two?
Yeah, so you are asking about the initial confidence of the networks in
That's
the
correct.
images. Okay. So actually, we test ourselves against the entire test set, which consists, in some cases, input images with a very high probability of correct classification, and others are with a much lower probability that is still the higher probability among all classes, but is lower than 90%, for example. So we do both.
Okay. If you don't mind me just clarifying my question, I'm just curious to know whether in general it will take more queries, the higher percent initial confidence, to find that adversarial pixel.
You're asking if we need more queries for images that initially are more than ever. Okay. So we didn't do this analysis, but I only can assume that if the initial confidence is higher, the number of queries would also be higher.
Thank you very much.
Hello, great talk, Kyung from KAIST. I'm just wondering if two images are similar to each other, then the attack point location is also similar?
The what?
If two images are similar to each other, for example, one for dog, the other one also for dog, but in this case, I'm just wondering if the attack point, this pixel location is also similar, for example, the head of dog or something.
Yeah, if two images are relatively similar, their attacks, their successful attacks would be similar. Yeah.
So do you have any intuition why this is similar?
Yeah, because the network, it's more about the weak spots of the network. For example, we can understand that in the perturbation in the center of the image are more likely to lead us to misclassification for a similar image where the object is in the center of the image.
Okay, thank you. Yeah.
Okay, as an outsider, I have a very quick question. Can you use your approach to improve the robustness of those networks against similar attacks?
That's a really, really good question. We have shown in the paper how can we use our approach for adversarial training. I must say that is a little bit an naive approach so far that we have shown in the paper, but definitely as a future research to understand how this approach of a program synthesis for generating adversarial attacks may lead us to a better robustness of neural networks.
Thank you.
Thank you.
Okay, if there are no more questions, let's thank Tom again.